So this is a new microphone and another try to produce some sound, and I hope that you can hear something now. Could you give me a feedback now through the chat? Ah, it's finally working. Wow. Yes. Ooh, so this was a tough one. I do this now every day, so I never had such a problem. Now I use another microphone and I hope it works. So okay, so I know that my microphone is gone. Okay, I just need to okay. Welcome to the course Traces in Hydrology, finally. So I understand that that you didn't hear anything so far. I just saw my funny face and my desperation trying to get this going. Maybe just a short comment. I will follow now the chat to see whether there is any problem. So if you have any question or problem, no sound for example, please just send me a short notice in the YouTube chat. So we'll just have a live stream now for today where I give the lecture. Just a short comment on the technical aspects. I had to use Adobe Connect because the system that we use at our university cannot be used for external students, and there was a problem with the system. So my name is Christoph Kölz, and I want to introduce tracer techniques to you. And I wanted to give this lecture much earlier, already in March, April, but because of the present conditions, this was not possible. Now, we try to have the lecture now, and as an online lecture, not in presence, I hope I can see you or meet you, especially if you're interested in artificial tracers soon. Now the lecture covers artificial tracers in hydrology and in hydrogeology. There is a question whether the video can be uploaded. Yes, I will cut it and remove the first 15 minutes of disaster without sound, and the edited video will be available in the on YouTube for a day or so, and then I will just have this as unlisted video and make it available on my channel in the NHI Learning Room. I will shortly introduce myself. I assume that you didn't hear it, my first introduction. So if you could hear me at that time already, just send me a short message through the chat. Otherwise, I will just do my presentation again. So my name is Christoph Kölz. I'm hydrologist. I've studied hydrology in Freiburg, and I have studied with Christian Leipungut, who is one of the fathers of tracer hydrology, artificial tracer hydrology. Christian Leipungut worked on tracer hydrology in the 80s and published this book, Traces in Hydrology. I also provide some chapters of this book. I will also try some technology that replaces the board for you. Just a second. I had to sacrifice my mouse to get a microphone, so but you should be able, oops, not this one, You should be able to see the book now, Traces in Hydrology, Christian Leibengut, Piotr Maluszewski, and myself, published at Wiley. After my studies in Freiburg, I studied hydrogeology in Würzburg with Peter Utluft. With Peter Utluft on groundwater recharge of the northwestern Kalahari in Namibia. This was a project with different disciplines: mineralogists, geologists, structural geologists, hydrogeologists, geomorphologists, on African geosciences. A very interesting PhD project in the graduate school. And after that, I've worked for some years in a company, unusual scientific career, but in a very innovative laboratory for isotopes, hydroisotope in Schweitenkirchen, where I have learned actually to apply isotope methods and tracer methods in water management and in water resources management in Germany and worldwide. I came back to the university in 2005 and spent 9 years in Freiburg on postdoc and as a research assistant. And since 2014, I'm professor for hydrology and international water management at the Technical University of Lübeck. Just a short confirmation: is the sound and picture okay now? So can you hear me well? And do you see the live stream well? I would be glad if you just could just give me a short confirmation through the YouTube chat, so that I'm sure that everything is working fine. Okay, so during the next 3 days, I would like to introduce tracers in hydrology, and there are actually 3 sections. The first one is a general introduction into what we are doing, the idea of tracer hydrology, the context, and the first day will also include an introduction to artificial tracers, basically. So I will introduce the different tools that we have in terms of tracers and instrumentation to do tracer experiments. Then on the second day, I will focus on modeling of tracer experiments. So we will discuss the advection dispersion equation in detail, and especially in relation to the application in artificial tracer hydrology. So you will learn how to actually design a tracer experiment, how to calculate the amount of tracer to be used. This is very important for different media, for soils, for rivers, for groundwater. And the third day will be dedicated to the technical planning of tracer experiments, which involves also the application. In Germany, you need to apply for the use of tracers, because our water is protected by Wasserhaushaltsgesetz, and if you want to apply tracers, you need to actually have a permission to do it. Very important. So I will show you how to do this. And the planning of tracer experiments is also very important to do a tracer experiment well. So you actually think through all the potential problems, how to inject, how to sample, how to measure, how to analyze, as a justification for actually adding a substance to the water. And this is also an excellent exercise for you to understand what you're doing. So let's start with the first topic. So it's a bit more complicated now because I don't have a mouse, but we will overcome these difficulties. The lecture is based on the textbook, as I showed already, of Leipungut, Maluszewski and Külz, and I shared chapters of this textbook in NHIDE, so you can actually see the the chapters, and you should read them as background information for this lecture. And the lecture, in addition to what I already said, properties, also highlights the data analysis, and of course you will have exercises to apply tracers. So I'll give you some practical exercises and questions, and you can actually solve them and check whether you understood these aspects of the lecture. Now, what are artificial tracers about? They are mainly used to understand hydrological systems in the context of tracer hydrology, or hydrogeological systems as well. The tracer approach is shown in this figure, and basically it goes back to system science. So we try to understand a system. The system is a catchment, a soil, an aquifer. And in order to understand this system, this mysterious system that we cannot elucidate, that we don't understand fully yet, we need a well-defined input. And the input can be an amount of water, rainfall event, it can be a concentration of a tracer, it can be also energy, anything, or an artificial tracer. And this well-defined input or input function is then transformed by the tracer. I see the exam. Very good. I'll just come back to the exam after the slide. We'll do it very quickly. Now, this input is then transformed to an output, and the output can be measured, which is a tracer concentration, it's a discharge, it's energy. In our case, it's mainly tracer concentration, so a concentration at an outlet of a river, beneath the soil, in a second well, downstream of the injection well. And from the transformation of the input, we actually learn something about the system. We can do this by inverse modeling, or using experimental methods, or a theoretical framework. And the lecture will actually teach you how to carry out such a stimulus, such an experiment, how to monitor and how to analyze data to get further knowledge about the system. Now, I promised you to talk about the exam. Of course, very important question. The exam consists of exercises, so you will get a task and you can work on this task in groups. These groups should not be larger than 2, maximum 3 people, students, and these students are then together in a group and have a task. The task that you will actually address and solve is to actually plan a tracer experiment and write a so-called Wasserrechtsantrag, which is the permit to carry out a tracer experiment. This exercise is very applied and practical and important, because you can only carry out a tracer experiment if you have a permit and if this permit is approved. And on the other side, you need to know everything about artificial tracers to write a successful permit, which means you need to identify the tracer. We'll talk about this today. Choose the right tracer, justify why you choose it. You need to calculate the amount of tracer that you want to use. You need to demonstrate when you will sample, what you will sample, how you will sample. In order to do that, you actually need to pre-model your experiment, and you need to demonstrate the analysis. So everything that we do in the lecture is actually required for Wasserrechtsantrag. You will get this assignment on after the 3rd lecture, so on Wednesday afternoon, and you'll have until Friday to submit it. This is sufficient. It's more time than enough. You will need half a day to do this. If you want to verify, check everything, write it down, maximum a day. So I'll give you the assignment on Wednesday, and you will have until Friday to submit it. Does this answer your question regarding the exams, or do you have more questions or doubts about the exam? I'll just watch the chat in the meantime. Okay, there is some delay because of the live stream, so I will just follow this. It takes a minute or so until a bit less, 20 seconds until I see the response. Just please confirm quickly when you are okay. How is group organization planned? I have on Friday another exam. Okay. Now, group organization is planned through the platform, so we will actually, I will give you an opportunity to choose groups. So there will be a tool on NHI where you can actually inscribe into a group. So there will be enough groups for the registered participants, and you can choose already today, tomorrow, the group that you want to be in, and then register for the group. So I would say we'll finalize the group registration until tomorrow evening, so that we have Wednesday to sort out some problems if there are any, and then we'll finalize the groups on Wednesday. Okay, there is an exam on Friday. In fact, yeah, there are several questions. There is an exam on Friday, so I have two possibilities. One is to actually limit this until Thursday evening, but you want to prepare for the exam. I don't like myself when other people extend their exams into my lecture, so of course I could extend this until next week Monday, but I just want to do this if I don't actually affect another lecture that would start on Monday, because I don't want to actually affect the work of my colleagues. So is there any conflict if I would extend the submission until next Monday with other lectures? So I would just follow the chat. If there is no objection, if there is no conflict with other courses, then I would actually extend the submission until next Monday, 9 o'clock. Then you would have the weekend. If you agree on that, we would do it this way. In order to be sure that we are on the same page, I will make a vote, and you will have the opportunity to just agree. There's a no in the chat, so, and from this no I conclude there is no conflict. Then we'll do it this way. You will have until next Monday. Okay, so because there is a slight delay between the live stream, between what I do here and what you see and the response, I suggest that I continue with the lecture. If you have questions, I will then pick them up, take notes, and reply to them. Otherwise, we have too much delay. But please ask questions, because I want that you participate actively and that you're involved. Don't hesitate to ask questions. Just might take half a minute for me to answer them, because I see them with some delay. So the tracer approach is a scientific method of coding and decoding information contained in water properties and artificial or environmental substances transported in water. So actually what I try to promote with this lecture is an approach, is a way of thinking, a way of solving problems in hydrology. So we try to learn more about how hydrological systems function. This is the whole idea. And there are several possibilities for doing that. You can use environmental tracers or artificial tracers. Environmental tracers are everything that the environment provides as an input function, as a tracer. You have already heard a lecture about this topic. So this can be O18, deuterium, carbon-14, nitrogen-15, carbon-13, noble gases, pollutants. So these are substances that we do not inject ourselves actively, but that are injected or that carry an input function by nature. Artificial tracers, on the other hand, are injected by us. So we actually add artificial tracers to the hydrological system. And this defines somehow and limits the field of application of both methods. And I like to refer to my own experience in this case. I learned artificial tracers first with Christian Leipengut. And we applied them to actually study the flow of water through a soil of 2 meters, the flow of water along a hill slope, the flow velocity in an aquifer, or the dispersion properties within a soil column in the laboratory. And you see that the scale of all these experiments is small. We talk about meters, tenths of meters, and the time scale is short. So we talk about minutes, hours, days, weeks. You would not make a tracer experiment that takes 3 years to complete. You simply don't have the time. Nobody has the patience. So artificial tracers are actually limited by the scale, by the time scale of the experiment, and therefore also by the spatial scale. So you would usually not make artificial tracer experiments over scales of kilometers or tens of kilometers or time scales of years. There are exceptions because artificial tracers are used in meteorology, and you can do mixing dispersion studies over cities to understand the dispersion of airflow with artificial tracers. And here you can actually, you may have spatial scales of kilometers, however you still have time scales of hours to days because the wind is much faster than groundwater. I learned to apply environmental tracers in Namibia during my PhD because in Namibia I simply could not apply artificial tracers. We are in a desert, a semi-arid region. So first of all, you don't have rainfall during most of the year, just during single and very short events. So you would have to actually tag these events, these floodwaters, in a desert during these 2 or 3 days of the year where you have floods. This is very, very difficult. Doesn't make much sense. And you don't have the time because water flows are very slow. So you actually have to rely on environmental tracers to do experiments. But in this graph, you see that they are both complementary. They form part of one graph. They are both used to understand hydrology and hydrological processes much better. And they both require modeling techniques and tools to be applied. And I would even say artificial tracers and environmental tracers are or should be complementary. I will tell you and teach you to not see these methods as completely separate methods or even antagonists that you can do just this or just that. When I plan an artificial tracer experiment, I usually use environmental tracers as well, at least as a backup in case my artificial tracer experiment fails, so that I have still something to work with. We'll go into more detail of the tracer methodology during the lecture. Now, How can traces be classified? Environmental traces are often environmental isotopes, stable isotopes of water, of carbon, of nitrogen, of sulfur, of boron. I mean, you can choose almost anything you want. These can be hydrochemical substances. So noble gases, but also hydrochemical compounds that dissolve in certain aquifers or that can be used to identify certain aquifers, like selenium, strontium, the strontium calcium ratio, the calcium magnesium ratio, chloride, the bromide chloride ratio, the boron chloride ratio. So hydrochemical substances, pollution traces, and the characteristic is that the spatial input is via precipitation and from geogenic sources. On the other hand, artificial traces are chemicals that are introduced into the water cycle at a certain time and point in space on purpose or by an accident. These can be biological substances, spores, drift substances, drift bodies to trace water, salts. The characteristic is that you have a punctual input and injection defined by time, place, and the hydrological situation. And then you have some that can be both, like SF6, which is both an environmental tracer because we produce SF6 on an industrial scale worldwide. It pollutes our atmosphere since 1950, and we can use the input function of SF6 to date groundwater actually. At the same time, we could also use SF6 as a point tracer, or CFCs. You wouldn't use CFCs as a tracer because it's really a pollutant. On the one hand, we have used CFCs for age dating of groundwater, and although we wouldn't inject them, they have been injected by accident or by pollution from companies, and they can still be used as such as a tracer. Now, there was a question in the chat. The grade will be determined out of the exam, yes. So you will submit the Wasserrechtsantrag or the permit. I will evaluate it. There will be an analytical evaluation. I will communicate before. I can do it now. How I will evaluate it. So the criteria are, and I can put this down, and I will define this again when I issue the assignment, that you choose the correct tracer, that you justify well why you choose it, that you do the amount calculation correctly and well. I mean, it doesn't need to be down to a milligram of tracer. That's not the point. The point is you need to have a clear, transparent method to do it that is justified, and that you demonstrate the analysis of the tracer. Okay, there are 2 or 3 more questions. So I will then grade or rate each of these aspects so that you understand how you got your grade, and these aspects will be integrated into one grade for the entire group. If the group work doesn't work for any reason, someone actually refuses to work or is not cooperating well, in that sad case that I hope will not happen, you have the right to claim which is your part of the assignment, and then I will then proceed. And I will try to always give options to split this, but I hope this is not the case. You should learn to work together, even if it's difficult sometimes. Is the module over after Monday, or do we realize a trace experiment in the field some other day? Yeah, we have done this in the past actually, and it was a lot of fun, and I think very, very helpful. So we will actually not be able to carry out the trace experiment now, but we will plan a trace experiment, and a real one. We already have several projects where we will do trace experiments, so the trace experiment that we plan is a realistic one and can actually be executed soon. So the answer is no, unfortunately we cannot do this now, and the module will be closed after you submit your permit. This is fair, otherwise you wait for your grades forever. However, you will actually witness and learn about how this real experiment that I will use for the exercise will be executed this winter, because we'll actually do one, and I will share the information by video, or I will share reports so that you see an outcome of what we're doing here. Now, must we write in English? Yeah, I didn't think about this, but we have some rules. So our rule is that the exam is always in the same language of the course. So, I mean, we have them in Lübeck, but I suggest we stick to this rule. So I give the course in English, and I would ask you to submit your exercise also in English. However, how to say, deficiencies in the proficiency of your English will not affect your grade. So I will really just grade the technical aspects, selection of tracer, calculation. So demonstrate this well by Excel, by sheets, by tables, and if your English is not perfect, this will not be a problem. But this is part of the trophy course, and this is why I would like to actually keep the course in English. If this is fine with you. Is there going to be the same course again in the coming winter semester? So I hope we are back on schedule. So I should give this course again next March, April. So I hope the result of this statement is not that the number of visitors drops to 0 in the next 5 minutes. Yes, I give this course every year. This is the plan, at least for the time being. And there should be another course next March, and how the course will be given depends on the conditions and the epidemic status that we have. So I really hope that there will be a presence course, but I can't promise it. Depends on force majeure. Okay, I hope I have answered the question so far, and I would just continue with the lecture. Now, I would like to make this a bit more specific, and now I can see the delay between what I actually film and the YouTube channel, because I see both here. Seems to be something like 30 seconds. So the current traces that we actually use are listed here. Yeah, we have a delay of more or less 30 seconds. So just to help you understand that between your question and my answer, there's at least 30 seconds delay, because I can just see your questions here on YouTube now. In the next slide, you see the environmental traces that I have already mentioned listed, and the artificial traces on the right hand side. You should know the left hand side more or less. Maybe there are some a bit new to you, something like yes, I will also come back to the schedule. There are some new traces like argon 39, krypton 85 that you might not have heard of so much before, but I will focus now on the right hand side. I just saw a question popping up. So the regular schedule for the lecture should be, we'll have 2 to 3 hours of lecture per day. 2 to 3 hours. So the lecture should be from 10 to 1. And I hope that tomorrow we will not face the same difficulties that we had today. So I'm quite sure, because we have something that works now, and maybe we can even revert to Adobe Connect tomorrow. So 10 to 1 will be the lecture, and you have material that you should study before, and you have some exercises that you should do afterwards. So core time is 10 to 1, and you should prepare the lecture by reviewing the chapters, by preparing yourself, by using the material, and you can do exercises after the lecture, and you should do them actually, where you test your understanding and knowledge on tracer selection, on the mount calculation. And this is an excellent preparation to the exercise or to the exam on late Wednesday, Thursday, because we will train each component individually. How do I select traces? What is the right tracer selection? It's day 1. How do I calculate the amounts for a tracer experiment day 2? And how do I analyze a trace experiment model calculated derived parameters day 3? And these are also the 3 components of the exam or exercise. No, there is no extra exam apart from the exercise. We have tried this, but it's difficult. An exam can also only be online, and I think it's not really fair, and the group work is the best way to actually evaluate whether you have learned this. So I suggest that we just give the grade based on the group work. Okay, I can ask you something. There is a possibility that I include exercises, and that I incorporate the results of the exercise into the grade. Usually you get good grades at these exercises, so it would be like 20 or 25% of the overall grade. So it gives you some comfort, and it also encourages you to actually do the exercises. So this is a possibility to actually incorporate exercises into the grade, but I would actually wait and to see your feedback on this idea. Would you like this idea? So then I would ask you just to comment this idea in the chat. Okay, so I will now discuss the artificial traces that we have and how they can be used. Now, of course, first of all, we have salts: sodium chloride, potassium chloride, lithium chloride, or borates that could be used as a tracer. Salts are simple. It's quite easy to justify how you use them. So there was one positive reply to incorporating the results of the exercises into the result, like with, I would suggest 25%. So you actually get some base grade. You can improve your grade by doing the exercises. Okay, I would do this unless there is protest, and if there is protest, you can actually express your protest in the chat, so that I know that I shouldn't do this. If there is no protest now in the next 15 minutes, I would actually proceed with this. Now, you could use salts. However, salts have a major advantage and this disadvantage. And this disadvantage is that you need a lot of salt. Why? Because the detection limit of salt is usually in the milligram range. So you have, if we talk in ppm, 1 ppm, 1 part per million, which is 1 out of a million molecules of salt that you could detect. However, we have most of these salts in our groundwater anyway, sodium chloride, potassium, lithium. So it is not sufficient to detect 1 milligram. We will have to have an increase that is at least 2 times the standard deviation of this salt. And we often have 15, 20, 30, even 100 milligram of salt in groundwater. So if we want to detect a signal from our tracer experiment, we have to have a response that is in the hundreds milligram range or even more. So we have a ratio injection to detection from 1 to 1,000. And this leads up to scenarios where we need not just kilos, but sometimes tons of salt to actually create a result. This is why salts can only be used at very small scales. So if we study the flow through a soil, maybe around a borehole, it's often used by engineering companies to detect whether a borehole is actually well sealed with bentonite. Yes, then you can actually use salt, but you would hardly use this in a groundwater scenario, groundwater aquifer. I will just demonstrate this very quickly to show you how difficult it is to use salt. And for that I switch to my board. Just a second. So I already start drawing. So now we have an aquifer. This is just a very simple sketch of an aquifer, and this aquifer, let's say, has a borehole here and a borehole there, and we inject here and we do the trace experiment there. Now let's just do some very simple assumptions. So let's study a length of 200 meters, which is not even much. Let's take a aquifer thickness of 40 meter, which is not even much. And let's consider a width of the problem of 100 meters, which is not even much. So we have a total volume without considering the sediments here of 200 by 100, which is 20,000, by 40, which is then 800,000. Now, of course, this aquifer is filled with sediments, so we have a pore space of 1/4. So we get around about 200,000 cubic meters of water in that aquifer. Now let's assume that we inject here and the dispersion is in the shape of a triangle. Let's assume that we actually try to spread the tracer over the full depth of the aquifer, which is a good idea to have complete mixing here. Otherwise we have a 3-dimensional problem. Now we just have a 2-dimensional problem. If this is a triangle, we can apply like the formula for triangles, G times H half. So this leads to a total volume of about 100,000 cubic meters that are tagged or marked with a tracer. Now if we want to increase the concentration of the tracer, assuming that it's fully dispersed over this area with a salt, and we have a, let's say, dilution ratio of 1 to 10,000 that is needed to detect the tracer, I don't take into account the density yet, this is the volume, then we would need at least something this divided by 10,000, so 10 tons times the density. So we would talk about tons of tracer that we need for such a case. And this is a very short, so 10 tons. And because we need to include the density of the tracer, which is much higher than the one of water, we talk about several tens of tons. And you see that this is not possible. We would need a truck with salty water injected, and nobody will like this, and it's also a logistic nightmare to do this. You will learn that if we use tracers instead, artificial tracers, fluorescent tracers, we just need milligrams or grams to do the same experiment successfully. The next category, can you please repeat how you achieved 100,000 cubic meters? Report is better. Okay, there is a little objection. So this is enough. We protect minorities. So I would then suggest that we actually just evaluate the report, and the exercises are for you to train. This is also good. So the exercises will not be graded. If they are wrong, doesn't matter in terms of grades, and you are free to just try and test whether you understood. I think that's good. It's fair. Now, how did I get 100,000 cubic meters? Okay, I will just repeat quickly. I presented a case of an aquifer that has a certain dimension, length, width, thickness. Now, I just calculate the total volume of that aquifer. So 200 times 100 is 20,000, times 40 is 800,000. 20,000 times 4, 80,000 times 10, 800,000. So this would be the total volume of water in that cube. However, this is an aquifer, so we have sediments with a porosity, and only 1/4 of that volume is actually filled with water. The rest is sediment. So instead of 800,000, I just have 1/4 of 800,000, which is 200,000. So in this aquifer of this dimension, we have 200,000 cubic meters of water. Of course, if you have an aquifer of another porosity, like a schist, it could be much less if you have a different lower porosity. So this is just an example for sediment. Now, I try to calculate the volume of the cone that is created by my injection. So I inject a tracer, and from that point it spreads like a triangle. It doesn't like mark the full width of the aquifer immediately. It spreads slowly, and I just assume that the spread is looks like a triangle. So we'll learn how to do this much nicer tomorrow. Now, if this is a triangle, this triangle, the area of the triangle can be calculated with G, and G is the width of the aquifer, which I defined as 100, times H, which is the length of the aquifer, divided by 2, which is just because we calculate the area of a triangle, which is then multiplied with the depth. And because G times H half is half of G times H, I need to divide my 200,000 cubic meters again by 2. So I get 100,000 cubic meters of water that are actually marked or traced by a salt if I inject into a borehole. I hope this was clear now, or clearer. I will just follow the chat to see whether this was actually clearer. Now, other artificial tracers are tritium. Tritium has been used as an artificial tracer. Tritium is a radioactive hydrogen isotope. So the hydrogen isotope with just one proton is hydrogen. The hydrogen isotope with a proton and a neutron is deuterium, which is a stable isotope. And if you have two neutrons, then you get tritium, and tritium is unstable, it's radioactive, and it decays with a half-life of 12.3 years. So every 12.3 years, the activity of tritium is reduced by 50%. Now, tritium has been used actually in hydrological studies in the 1970s, in the 1980s, but if you want to use tritium in a laboratory, you need permits to handle radioactive substances. You need to be trained to do it. You need to actually make sure that you do not contaminate yourself, material, other people, the environment. And there is a lot of societal concern about tritium because it's a radioactive substance. So although tritium is a perfect tracer, it behaves exactly like water. It's very easy to detect. It has many advantages. It is not popular to actually apply tritium at all. So if you have tritium in the environment because of a research reactor releasing tritium, you can use it from the injection point as a tracer, but you would rarely or almost never in modern times make trace experiments with tritium unless you are in a laboratory at a laboratory scale or working at a research center which has the capacity to handle radioactive substances anyway, like GSF or KIT and Karlsruhe, who actually have departments working with radioactive substances. If this is not the case, I would advise you not to use tritium anymore. You can use drifting particles, but obviously this is associated with many problems. There are now some sensors that can actually track the GPS location and measure temperature and pressure, and you can actually throw them into water and track them. However, they are too big, and in that case they can get stuck. There is deviation, but it can be practical to study the flow in irrigation canals or in drainage channels, even in urban contexts in some cases. Christian Leipegut has worked a lot on spores. So spores are these tiny little spores. I don't know how to explain them. Seeds of fan leaves. And the idea is that, first of all, they have beautiful structures and you can actually detect them with microscopes. And there are many different ones. So you could actually inject several different spores and then count them under a microscope and get some additional information. So this is interesting actually, but it is only useful in karst studies. So if you study a karst aquifer, yes, good idea, because you have karst channels and voids that are large enough to actually allow a full transport of the spore. However, if you work in a sediment sandy aquifer, it's not a good idea because the transport is delayed too much. You can even add fluorescent dyes to these spores, so you actually pour them into a solution with fluorescent dye, and they will actually pick up the color, which makes the detection of these spores much easier. So you have actually fluorescent spores that can be detected easily under the microscope, even counted under the microscope. This is a possibility. You could actually use also bacteria, viruses, and other biological particles in tracer studies. However, again, there is a safety issue. You need to be able to handle this. However, you should know about this because many clinics actually work with fluorescent dyes to tag and to trace cells, and they have the knowledge to do this. However, getting a permit to inject bacteria into a river is again difficult. So we actually end up with a group of tracers that do not have all these disadvantages of salts, too much substance, spores, still nice, but can just be used in karst aquifers, bacteria, viruses, safety concerns, or tritium, safety concerns. And these are fluorescent tracers. And they actually are the focus of the lecture, and they have many advantages. And I will name them. It's uranine, eosine, naphthionate, pyranine, amidorhodamine, and all the rhodamines. There are more. There are about 10 or 12 that are common. However, these are the most common ones, by far the most common ones. And I will not discuss the rhodamines because there is some concern about using them, so I will just focus on amidorhodamine and sulforhodamine, which are the safe variants of the rhodamines. So let's go into this in more detail. Where can we apply tracers? In which areas actually of hydrology? The following graph that I will just comment quickly, you can study this in more detail, gives an overview of what you use, which tracers you use for which applications. And these applications are given in columns like atmospheric water, surface water, soil and saturated zone, groundwater, glacier and snow, catchment hydrology, and a special application. Now, you see these different applications, and let's just focus now on groundwater for the time being. And you see here the different aspects of what can be done with tracers. You see it's quite complete. So you can do discharge measurements with tracers. We'll also talk about this. You can study hydraulic connections. Is this spring connected to a possible pollution source? Many of the projects that I did in Bavaria were exactly this problem. There was a spring, and in the spring there were E. coli coliform bacteria. So the water supply had to be shut down, and the health department said you have to find the source of the pollutant of the contamination. There were 2 or 3 candidates: a farm with pigs and dump for manure, another farm, a street, a waste dump, let's say. So 3 candidates. And what you do is actually you visit the place, you inspect the place, and you add 3 different tracers to each of the potential sources. You inject, you wait, you measure in the spring until you detect something. And then first of all, you know where you get the pollution from, whether it's from the farm or the street or the waste dump. And you can also detect when the trace arrives and how much, the breakthrough curve, so you actually learn about this hydraulic connection. So you can study flow paths. There are several articles about this that we have published and also in the book. There are some that can just be done with environmental tracers like age dating or altitude detection. But you can study runoff processes, processes in hill slopes, and so on. Of course, you can also calculate permeabilities of substances. So, in conclusion, tracer applications span a wide range of compartments and purposes, from basin delineation to very specific hydraulic questions. But these can be subdivided into different compartments. So application of tracers in rivers, lakes, glaciers, groundwater, or soil. Different functions or purposes like velocity estimation, discharge measurement, and protection zones, and different scales, like from centimeters to macro scale, more than 1,000 meters, I would say. In general, we can say that artificial tracer applications are limited to cases where the time of the experiment takes less than 3 months and where the scale is less than a kilometer. From my experience, there's no administration in Germany that has patience to wait for a breakthrough of a tracer that takes more than 3 months. People will get impatient. They will say, let's stop the experiment. So in a research context, you can do this. You can actually make a trace experiment and wait for the result next year. But in a practical context where people wait for results, never. So you should only do a trace experiment if you would expect the result within 3 months, a complete result. Otherwise, I would actually use environmental tracers and tell the customer I would use another methodology. This is probably not going to work. I have done trace experiments where we waited for a year to measure. For example, in Namibia, we have injected tracer into an alluvial channel, and I came back a year later and I sampled. We got perfect results. We were very happy. But this was a research context where I myself decided, okay, I can wait for a year. But if others wait for results, they will not wait for more than 3 months usually, very rarely. There is an experiment though where we have done this and where we actually monitor for more than a decade, and this was a very interesting idea. Geothermal energy, you need 2 boreholes. They drilled. One is for actually getting the hot water out, which is then used for deep geothermal energy. So we have hot water, actually 80 degrees, so out, and the cool water is then re-injected. Now you hope that the cool water is actually flowing back without a hydraulic shortcut to provide enough time for reheating the water completely. Now, in order to prove that there is no hydraulic connection or shortcut between the injection and the abstraction borehole, the customer had the idea to actually inject an artificial tracer. So we have injected an artificial tracer in one of the boreholes, the injection borehole, and we have monitored for this tracer in the abstraction borehole, and in case we would see any of the tracer in the abstraction borehole, we would know that there is a hydraulic shortcut. So I did this when I worked for the isotope laboratory, and we waited, we went there once a year or twice a year, took the samples. We never detected anything, but this is a nice example of a trace experiment that took more than a year, that was designed to take several years, but very rare occasion. Often we conceptualize our hydrological system before we do a trace experiment. So we subdivide it into different compartments, like subcatchments or springs and lakes, and we want to study the interconnections between these compartments. So this doesn't work in sedimentary aquifers. We still don't have enough time. But if you work in the high mountains, in the Alps, and then the hydrology is quick enough often to actually provide results even with artificial traces. So artificial traces are an option in fractured aquifers because the the volume of water is much lower because of low porosity, and in high mountains because you have faster flow, higher gradients, and you can actually get results quickly even in mountains at larger scales. Now this is a nice study that I have carried out in 1915 or 16, I'm not so sure anymore. and I will just show you how tracer spreads. This was an experiment that we have done in Berlin in a natural in a structure to clean water just by ultraviolet radiation in an open pond and by filtration. So what you see here in the picture is actually a surface reservoir that is used to disinfect water, to clean water in an open structure. So the lower part is actually a reservoir that is half a meter, 70 centimeters deep. The idea is that ultraviolet radiation destroys bacteria and anything that would pollute the water, and then the water actually flows into these upper structures. I don't know whether you can see my pointer right away. Just try to show this. And yeah, I think it doesn't work. So in the upper right and upper left, you have two sediment structures filled with sand and gravel, to which the water actually is filtered. And now we wanted to study how this structure works, and there was some concern that the mixing was not complete. I took this picture from a crane high above this. I was really scared when I took the pictures. It was very shaky, and so I was on a crane and took a picture down, and there's one of my colleagues sitting there on this island with buckets filled with tracer. We took the picture of these tracers to actually then correlate the color in these buckets of different concentrations with the color of the plume. So now let's just follow this. You see now the trace experiment. We have added Euro 9 to this pump system, and you can see now how this spreads, how the dispersion takes place, and how the tracer actually now reaches the reservoir. And if we go back, you can also see, this was not what I wanted. You can see where the mixing is not complete, where you have these steps on the right hand side, and you can study the functioning of the system actually, and this was the whole idea. Now this is an application where too much tracer was used. Usually we do tracer experiments in a way that you don't see the tracer at all, but in this case it didn't matter. The customer wanted to see something, so we overdosed heavily, I would say by a factor of 1,000, because it was okay, and it was actually even desired to have a visible result. Now the interesting thing is, with the buckets we could actually calibrate different concentrations for colors, and this is a calibrated picture that we just got from image processing or image analysis. So I have actually carried out a correlation of the RGB channels and calculated the concentration from the RGB values of the picture, and by this I could actually translate the picture into real concentrations, which you see here. And you can do this for all the processes. Red means high concentration, blue means low concentration. Another example is the application of tracers in lakes. So lakes actually have an interesting phenomenon that I will just try to draw in a second. And this phenomenon is that they have an auto-rotation. So just a second. Okay. So I will start the camera, and okay. So you see my microphone now. Okay, so let's assume we have a lake. This is the lake, and this lake, sorry, don't see the right hand side. Let's just move this. Okay, so this lake has an inlet, so Q1 flowing into the lake here, and an outlet. Q2 should be the same in steady state conditions. Now, in lakes, often there is, depends on the size, an auto-rotation. So on the northern hemisphere, Coriolis forces actually lead to a right turn. So we actually get this type of rotation in the lake. And this is important because let's assume that you have a water supply and you want to abstract water from here at a certain depth in the lake. Water supply, you don't see this, water supply. Now let's also assume that we have a potential source of pollution, maybe, I don't know, before it was actually a farm that was close to a lake. Then this scenario is actually worse than having the abstraction point here, because in that case the water would actually have more time and opportunity to disperse before it reaches this abstraction point. So if you actually study the water quality in a lake, trace experiments are very helpful to understand the auto-rotation and the movement of flow within the lake, and tracers have been used to do such studies in the past. So let's do it. So a bit more complicated because I don't have a mouse. So okay, and you see such an experiment here. I think it was a lake in Slovenia. Trace experiment carried out by Christian Leifengut. Oh. Okay, this is an example of an injection into a small creek or small river by Jochen Wenninger, if I'm not mistaken. And this is to study simply the velocity of flow, but also the dispersion, or to do a discharge measurement in unregular channel. Because try to measure discharge here with a odd propeller. Very difficult, I would say impossible, because it's too shallow. However, if you add tracer, you can do a nice measurement of this of the discharge in this very shallow channel easily with your tracer. Glaciers. So Euro 9 has been used in glacier studies. You know that especially now, because of climate change, glaciers are melting. They become temperate glaciers, so they have streams of water at their bottom, which is very important for their movement itself, for the movement of the glacier mass. However, this water that is flowing beneath the glacier can also have dramatic, catastrophic releases of water that can endanger villages downstream. In order to understand the release of water from glaciers, but also the flow processes in the glacier, it can be very helpful to study glaciers with tracers. Now, I would like to make a little break now, a break of 5 minutes or so until 3 o'clock. So I will just stop the lecture now. I think I keep the live stream on, and we will continue in 5 minutes. So it's 2:54, 55 now, and after a small break of 5 minutes, I will continue the lecture and dive into tracer properties. So see you in a minute. So I'm back. And we want to okay, could you just confirm that the sound is okay and that you hear me well in a second, so that I know that technology works? And we would like for you to plan the time better. I will now give a second lecture that will last at least an hour, maybe a bit more, but we should be done at 4:30 latest. So today 4:30, if you have other commitments, so a lecture will not go longer than 4:30. Yeah, what we would like to do now is have a closer look at the tracer substances at the fluorescent dyes. So first of all, we use fluorescence. I will prepare a little video of the fluors of the spectrometer that we have in our lab, that you can actually see this. And basically what we do is we just measure with light. So we need a light source. The light source is a lamp of a specific wavelength, LED, or a lamp with filters, a lamp that produces a very well-defined input and from which I actually cut a certain wavelength with a filter. There are also fluorometers, spectropluorometers that can produce a range of wavelength that have a prisma, or nowadays in modern devices a grating that actually splits light into a spectrum of wavelength with which I could actually scan through all the wavelength from A to omega. Now usually we look at the visual light at the spectrum from something like 380 to 750 nanometers. Sometimes we include UV light. I have an experiment now on Thursday where we actually study the fluorescence of polycyclic aromatic hydrocarbons, which requires UV light excitation. Now, of course, you know that this is just a small part of the full spectrum of electromagnetic waves. The traces that I will discuss now are part of the fluorescent dyes. This is just again a kind of subdivision into different groups. The first one are the fluorescent dyes. Just to make you familiar with the names, naphthionate is a brightener, something that you wash your clothes with so that when you go to a discotheque they are shining white and bluish to produce the impression that they are clean. Pyranine, which is yellowish, comes from pyros, fire, has a color like fire. Uranine is the most common one. Sometimes when you use the word uranine, people get scared because it sounds like uranium. So if you send a permit to people who are not so well educated in terms of tracer hydrology, I would always use the technical term natrium fluorescein, because natrium fluorescein is much more innocent and doesn't evoke this association with uranium. Eosine from Eos, sun, is a bright tracer, is quite similar to uranine. Amidorhodamine is a red tracer. This is the safe variant of the rhodamines and can be used in rivers. Now, I've discussed the salt tracers. They can be very practical in case you run out of tracers, or sometimes, as I said, at small scale. Bromide has the big advantage that there are bromide sensors, so for small experiments this can be helpful. And then the radioactive or activable tracers, quite uncommon. There is still the possibility to use stable isotopes also as an artificial tracer, heavy water, deuterated water, but this is expensive. So if you want to buy a kilo of deuterium, it's about 4,000 euro, I think. So quite difficult to convince somebody to pay an experiment with deuterium. Now, The fluorescent dyes that we can use, they have properties, and these properties are important for their use. And this table gives you an overview of the most important properties of fluorescent dyes per tracer. Now, the most prominent property is the excitation and emission wavelength. What is this? Every tracer fluorescent dye is actually gets excited about certain wavelength. This is light of wavelength that this substance can absorb because of its chemical structure, and it will only absorb photons of this specific wavelength. So it will, or energy, it will only absorb a certain wavelength. For example, naphthenite will only absorb light at 325 nanometers, which is ultraviolet light. So naphthenite doesn't react to 400, 420 or 280. It reacts to 325 nanometer light. This light will then actually elevate the molecule to an activated state, and the molecule will release a photon of the emission wavelength with 420 nanometers of wavelength, in this case much longer. Now, this unique combination of the excitation wavelength on the one hand side and the emission wavelength on the other hand makes the measurement of fluorescent dyes so nice and easy, because you just need a light source of 325, and actually you will only activate naphthenate and not other tracers. And you need a sensor that has a window or filter of like 415 to 425 nanometers, and it will only see naphthenate. And this unique combination of emission and excitation wavelengths makes the measurement of fluorescent dyes very specific. And by the way, it's also sensitive, because you could actually measure naphthenate in a mixture of other tracers. As long as you don't have another tracer with the same or similar excitation and emission wavelength, they will just be dark black. You will not see them. You will just see the naphthenate in this mixture of tracers. This is what makes them so interesting. Now you see the chemical name, the compound class, and the chemical formula, and the molecular weight. You see it's a heavy molecule, 245 grams per mole, which is quite a heavy molecule. But still, naphthenate behaves well in water. It behaves like water. It doesn't sorb. It's not strongly degraded. And I will discuss all these other properties also, but this is very important. Now, I will not go through each of them. You see now the emission and excitation wavelength for pyranine, uranine, eosine, and so on. I will just highlight 2 or 3 important things. So you should really remember the excitation and emission wavelength of uranine, which is 491 excitation wavelength and 516 emission. So there's a difference of more or less 20 nanometers. This is important because this is the most common tracer. And you should also remember, like the amidorhodamine, which is reddish, has a red color with a wavelength of 530 to 555. For the others, I would just recommend that you have a look at them. You can buy these tracers from Merck or from, don't want to do advertising, from handlers of chemical substances. The price per 500 gram or kilo is usually 100 euro, 200 euro, so in this order of magnitude. So we always plan more or less 500 euro cost per experiment, because most of the time the amount of tracer that you need if you use fluorescent dyes is grams or milligrams. It's not really significant. Now this is how these traces look like, and you see why they are fluorescent dyes. They have a chemical structure of this benzoyl ring that actually can absorb photons, get activated, and release energy or photons again. So the special chemical structure of these substances is the reason why they have fluorescence. And here you also see why uranine is called natrium fluorescein, because natrium fluorescein or sodium fluorescein, because it's a salt of sodium. In fact, except for rhodamine B, they are all salts of sodium. This is why they are also quite soluble in water, so they have a high solubility. And yes, a summary of the excitation and emission wavelengths is given in this graph. So you see again the naftionet that I have discussed in more detail, from 320 to 420. You see the uranine that I have mentioned from 491 to 516. You see the sulfurrhodamine that I have also explicitly mentioned from 530 to 555. And you see the other traces. Now if you choose not just one but several traces, you should try to actually choose them in a way that they do not overlap. So you can easily combine naftionet with uranine because they have completely different emission and excitation wavelengths. You can also combine uranine and rhodamines, although there are other tracer properties that may not suggest that this is a good idea. Now you see also another dimension in this graph, which is the efficiency. So uranine is the most efficient tracer. The light invested, if you want, is re-emitted with a very high efficiency. Now this is scaled to uranine, so compared to uranine it's the most efficient tracer. The others have efficiencies of 20 to 30, tinopal, T, just of 5%, which means that you need 5 times more naftionate to get the same fluorescence brightness, if you want, compared to uranine. This is again what makes uranine one of the most interesting tracers for artificial tracer applications. Now, the spectra are given here, so this is what you see, and I will explain the principle a little bit. So if you actually have uranine, we know that you have an excitation at 491 and emission at 560, more or less. So there is a difference of 25 nanometers. So if you have a good device that actually can change the excitation wavelength with the prisma that you turn, and with which you can also define that you always want to measure the excitation, so the light that is produced by fluorescence at a delta L shift, in this case 22, I calculated 25, so at this shift you can actually now produce light from 350 nanometers to 700 nanometers, and you have your sensor monitoring at plus 22 or plus 25 nanometers. And when you get to 491 excitation, you will see a perfect emission at 516 at this delta L. And with this combination of excitation spectrum and emission spectrum, you can identify uranine very clearly and separate it from all the other traces that have sometimes different distances, like naftionate, or different emission wavelengths. So these are the spectra that you get. This procedure is called double scan. So you scan through all the wavelengths for emission and for excitation and for emission. Now, for each tracer, there's a kind of fact sheet. Again, including the formula, the name, there are different chemical names, and the molecular weight. Here you have the fact sheet for uranine. That is also called acid yellow, or CI45350. This is the color index. And you will get more tables on other properties during the lecture. Now you see here the injection of naphthionate and the result. The result is that with some imagination you can see a bluish shiny appearance of the water. So this is the fluorescence that is caused by sunlight, and the sunlight includes ultraviolet radiation of 325 nanometers, and actually it creates this bluish light that you know from discotheques, from your white shirts that have been washed with naphthionate additives, maybe. Now, we use instruments to measure this fluorescence, spectrometers, to actually get the result. So here the fact sheets are expanded. I would just ask you to have a look at them. Another thing that we should actually keep in mind is that the molecular weights are always high, 245 to more than 600 grams per mole. And if we look at the chemical formula, they are composed of carbon, hydrogen, sodium, oxygen, and sulfur only. Now, I would prefer the ones that do not have bromides or chlorides in them, because this is safer. So the rhodamines are actually questionable in certain aspects. So I would prefer the puranine and the sulforhodamine G extra. Yeah, if we just confirm this, we see that the eosine has some bromide in it. Actually, 2. Bromide can be a problem because in water with higher amounts of dissolved organic substances, and in case of ozone treatment, you could actually produce a reaction between bromide and the organic substances that you do not want. So I would actually refrain from using bromide bearing or containing substances if there is ozonation in the water supply somewhere. Now this is an experiment where we have used sulforhodamine G. There is a question, sorry for not picking it up immediately. What does mixing of 2 more traces imply? Will this affect their chemical structure? Usually not. In some cases it may, but usually not. Usually they are, I would say, miscible, and the only problem is the detection, the different wavelengths. They should not affect each other. Usually tracer combinations are only done if you want to get more information from an experiment, but you would only combine 2 or 3, and it's usually very well thought that you can actually really analyze all the traces at the same time without interference. So usually practically we just use a limited number of tracer combinations. But the chemical reaction in between them is actually not the problem usually. This is has not been observed. In this case, we have used sulforhodamine, and I already want to introduce the idea. Uranine is used for groundwater, not for surface water. Why? It does not interact with the aquifer matrix, it does not sorb, but it is sensitive to light. Rhodamines, sulforhodamine, especially amidorhodamine, is used for surface water. Why? It is not affected by sunlight that much, to a much lower extent, almost not at the time scale of our experiments, but unfortunately it interacts with sediments, it's sorbed. So when you do measurements in rivers at the surface, where absorption is not the key problem, then you can use sulfurrhodamine. Obviously here we have sediment in the water. It's not perfect, but there was no other choice. If you work in groundwater, you should use uranine. It's wrong to use sulfurrhodamine in groundwater because most of it will actually be sorbed on the sediment. It's wrong to use uranine in surface water. This is like a beginner's mistake. There might be situations or cases where you have to use uranine in surface water because there are no other options and so on, but you shouldn't in a normal case. Uranine, groundwater, sulfurrhodamine, amidorhodamine, groundwater, all the surface water. All the rhodamines for surface water, because they are not sensitive to light but sorptive. Uranine, usine, pyranine can be used in groundwater, naphthionate as well. Okay. Now, the first property that we have discussed is the wavelength of excitation and emission. The second very important property of a tracer is the detection limit. So what is the detection limit of different tracers? And again, the most sensitive detection is possible for uranine or natrium fluorescein. We can detect down to 0.002 milligram per cubic meter or microgram per liter. So if we actually translate this, milligram per cubic meter or microgram per liter, we have 0.002. We can actually detect 2 nanograms of the substance in the best case. 2 nanograms of uranine in water. And we do not need HPLC, ion chromatography, or mass spectrometer. We can just detect this with a spectrometer, with a light source and a light sensor, a spectrometer for a specific wavelength. So the instrumentation is also much cheaper. And the relative fluorescence is by definition 100 because uranine is the best one. Now, if we look at the others, usine has a lower detection, or higher detection limit if you want, factor 10 higher, and the relative fluorescence is also a factor of 10 lower. So you need 100 times more, actually. Let's go to the others that we could apply in groundwater. Pyranine, 0.02, like usine. Efficiency is a bit higher, so we need something like relative fluorescence is 1/5 of uranine. Detection limit is 10 times higher, so factor 50 more substance. Naphthionate, detection limit again worse because ultraviolet is more difficult to detect. You have more scattering of the wavelength. Relative fluorescence is factor 5 higher. Detection limit is, you see, factor 100 higher, so 500 times more substance. Now if you look at the surface water tracers, amidorhodamine G extra has also a low detection limit, similar to uranine. Perfect. Relative fluorescence is 1/3 more or less of uranine, so 3 times more substance. So the champions here are uranine for groundwater and amidorhodamine G extra for surface water. If you need other options, there are variants of the rhodamines. I would not use the so-called rhodamine WT water tracer, which is still used in the United States, but which is known to be cancerogenic. I would not use it, really not use it. Most of the instruments still have the emission excitation wavelength for rhodamine WT, but we know since 40 years that it's cancerogenic. We should move on. So we should use amidorhodamine, G extra, or sulfurrhodamine, but not the classical rhodamines and rhodamine Bs and WTs water tracers. Simply not. Now, if we want to consider other groundwater tracers, we have pyranine, naphthionate, but we need higher amounts because detection limit is higher. Okay, so this table is important in terms of properties. Now, I already told you about this synchron scan. This is the most sensitive measurement. So we actually have a light source that scans through all the wavelengths, let's say from 400 to 600 nanometers. There are spectrometers that you can program to do this on a regular basis. So you scan, you change the wavelength for excitation, and you have a mobile filter with which you can actually scan also through all the emission wavelengths. If you do this, you see on the one hand the emission, on the other hand the excitation, and you get this dashed curve, the synchron scan, with this, which is very sharp and specific for Euro 9, and you are sure that you just get Euro 9 and no other tracer. Now, the height of this fluorescence, the intensity, is actually then calibrated. So we prepare several bottles with known concentration in the lab, where we add the tracer to water, dilute it, and we measure this before the experiment at different concentrations. And when we get the bottles in from our experiment, we measure again, and we use this calibration curve so we can translate intensity to concentration of the tracer. This is how it works. Now, you can use the knowledge about different emission and excitation wavelengths to separate tracers, to separate a mixture of tracers. So here we have a tracer mixture of Euro 9, sulforhodamine B, and the tracer mixture. And by just using the excitation wavelength of Euro 9, you can actually separate these two curves, these two tracers, and measure them next to each other, especially with the synchro scan. So let's just remember sulforhodamine B, and let's go back to the table. And it's not in here, unfortunately. It's also not in here. This is not good, but it's in here. So we have SRG. So we actually get a excitation at 535, 555. So we would actually not get, we have a very similar delta lambda, but we have different total excitation wavelengths. So we get peaks at different wavelengths if we make a spectral scan, and from the intensities that we get of the curve, we will actually be able to measure both concentrations in the tracer mixture. However, it's very rare that you use Euro 9 and sulforhodamine B in the same sample, because one is for groundwater, one is for surface water. So usually you do not combine these two. Okay, this is again a summary from the textbook on the different wavelengths, quite similar to the other one, but for some additional tracers. So you can just use this as a reference if you are asked to choose different tracers. Now, the next chapter in terms of properties is the pH dependency. And this is important and often forgotten. People who know a little bit about tracers but not so much, they usually neglect this aspect, and you shouldn't. The fluorescence is actually sensitive to the pH value of the water. And the best fluorescence is achieved at a pH of 8.2 for Euro 9. There is a chemical reason for this, like at different pHs, there are different equilibrium states of the molecule. The practical impact of this is that there is a pH dependency of the tracer. Now, why is this important? 20 years ago, most of the trace experiments were just done by taking sample bottles, bringing them to the lab. And in the lab, someone expert, knowing the device very well and the traces very well, measured the sample. So everybody familiar with measuring fluorescent dyes knew that he had to actually buffer the water to produce a stable pH at 8.2 to have the best possible measurement of uranine. So he did it by adding a buffer substance, creating a pH of 8.2, and he got a very nice, sensitive, reproducible measurement at pH 8.2. Nowadays, we have more and more cheap LED fluorometers. Yeah, cheap is relative, so you still pay between 4,000 and 10,000 euro for such a fluorometer, but it's much cheaper than a spectral fluorometer, which costs 30 to 50,000 euro. Now, you can buy these field devices to actually measure fluorescence in the field, and it's very tempting to do it because you get measurements online all the time, every second, every minute, whatever you want, registered on a data logger. However, if your water has a pH of lower than 8, which often it has, your measurement will not be carried out at the highest possible efficiency of the experiment. And if you have water that has a pH of 5, 5.5, 6, 4.5, which is sometimes the case in granites or in schist or in peat or in an environment that creates water of low pH, then you will maybe not even measure any fluorescence, and not because it's not there, it's not because the tracer didn't arrive, but the tracer arrived in a state that doesn't have fluorescence. So that's bad. Now, before we go into this, let's have an overlook of the 10 key properties of tracers. So artificial tracers should have these 10 characteristics. They should be highly soluble in water. I mean, come on, if you need to dissolve a substance that has a solubility of, I don't know, micrograms per liter, it's difficult to bring your tracer into the water. High solubility. It should have a high fluorescence intensity. So you should actually get a high fluorescence with the smallest amount of tracer possible. Should have a low detection limit. It should have a low pH dependence. It should have a low temperature dependence. It should be photolytically stable, so not be degraded by sunlight. It should not have strong sorption, and it should be chemically stable. The question was there, can we mix tracers? Yes, if they are chemically stable. They don't interact? Yes. It should not be toxic, very important, and it should be cheap. So these are the 10 dimensions in which you evaluate tracer properties. This is the key list that you evaluate. Now, in some cases, you can actually accept that the photolytic stability is not perfect, like for uranine, if you work in groundwater or in caves or cast caves. In some cases, you can accept pH dependence if you are able to correct this afterwards by changing the pH. And the fluorescence with uranine can actually be restored. You can get it back by increasing the pH. So if you have all these characteristics, you have a perfect, ideal, or we also say conservative tracer. Yeah. So conservative means it doesn't change. It's not political. So ideal tracers or conservative tracers have these 10 properties. Now let's check the detection limit. You already know that the detection limit for uranine is quite low. Here you even get 0.001, so even half of what we had before. Amidorhodamine is comparable, and then you have the pyronines, rhodamines that we shouldn't use, and the sulforhodamine B. And then again, in order of magnitude less detectable is enough to emit. Relative fluorescence, we have repeated this several times, and excitation emission wavelengths. You find these properties in the context in the chapter 3 of chapter 3. It's not chapter 3. I think it's chapter 4 of the book on tracer properties. Now, you should also know that the detection limit depends on the properties of water. So if you have clean groundwater, detection is easier. If you have a dirty surface water full of algae, maybe some dissolved organic carbon, detection is more difficult because you have more scattering, more background. And you should always check the background. So in this curve, you see the spectral signal of the sample in different waters, drinking water, surface water, and the background concentration or background scattering is shown here, the lower curve, and like the extra fluorescence produced by a tracer is on top of that. And of course, only the difference can be used for detection. Now, the calibration, as I said, is usually done in the lab before, and you should be careful to evaluate how you do the calibration. So I would recommend to do the calibration already with the water. So before you do the experiment, it's a good idea to go to the field, to take water and to measure it. This is your zero sample, and you prove that there is no uranine in the water before your experiment. It is actually the case that in some areas, in some cases, you already have these traces in your water before you have a background concentration. There can be several reasons. Pollution, uranine or fluorescein is actually used in some products, cleaning products, to make them look fresh like lemon. So in some cleaning products we have traces of uranine, which gives them a yellowish color, a yellow color, bright yellow color, which is associated with freshness for some reason. Now, if people use this and this gets into your river or into the water cycle, you actually have uranine in the sample even before you do the experiment. Now, another reason can be that there are other hydrologists doing trace experiments. Unfortunately, this is why there is a database of trace experiments in Bavaria, in Baden-Württemberg. In some countries or states, this is not the case, and this can actually lead to interference with previous experiments. So if a trace experiment has been done at this site before, then you can actually still find some uranine in the groundwater. So you should check the database for previous experiments, and you should always use your substance carefully, and you should actually never use the substance without indicating it. First of all, it's illegal, and second, you might actually spoil the trace experiment of somebody else. Now, you bring the zero sample to the lab, and then you add tracer to create a series, let's say 7 samples, 10 samples of different concentration over the linear range, and you measure them, and you get the intensity for a known concentration, and this becomes your concentration curve. You will observe that at very, very low concentrations below the detection limit, the curve is not linear anymore, so you cannot actually extend the curve below that. And at very, very high concentrations, it will not be linear either, but we all hope that you will never have a sample with that concentration, because it would mean that your calculation of tracer mass has been wrong and failed and doomed, and you have just polluted a river and made it look yellow or red, which nobody wants. At the end of the day, you should get a calibrated curve like the right-hand side with a linear relationship which can be used. Y equals a constant plus a slope with a given r square, which can be used for converting measured intensities to concentrations reliably. And if you do this already with your real water, first of all, you know whether there was already tracer inside, and second, you get a calibration with the same water that your tracer will be in later on. Now, the pH dependency of uranine is shown here, and you see two problems. The first problem is that the fluorescence actually decreases. So you see here that at pH 9 you have the highest intensity, and at higher pH the intensity is going down further and lower, further and further. And the second problem is that you get a slight shift in the excitation wavelength, which is also bad, because you expect the excitation at a certain wavelength and it's slightly shifted. So you should measure at pH of 8 or more. And this is not a problem if you know this, if you're in the lab. But if you don't know this and you actually measure in the field online, you might actually really miss a curve with online spectrometers, because simply pH is too low, as I said before. Now, the pH dependency for eosine is shown here. The same phenomenon, decrease of the fluorescence. There is no noticeable shift of the main fluorescent peak. The same for puronine, and here we see something really nasty. We have a known excitation at 450 at pH 10 and 9, and if we go below pH 8 we get a second peak, and this peak grows stronger and stronger, and the first fluorescence at 450 disappears. It's actually quenched, disappears, and we get a second peak at 400 nanometers. So this is really bad. However, it can be good, because you could use it to actually suppress the fluorescence at 445, 55, I think, and measure uranine. You can't really, because you will also quench the one of uranine, so this doesn't work. So you should simply just be aware of it and make sure that it doesn't happen to you, because there's also no interference with uranine in this case. You could just quench it for another tracer that is not actually affected by pH so much. So with puronine you really need to be careful to control the pH during your measurement. Just a little question. I'm talking here to the camera. Are you still okay? Do you follow? Is the sound and quality of the picture okay? Do you follow? Is the speed okay? So if you are okay in your seat and enjoy, just give me a little feedback that I know that everything is fine. I can't see you, and because I can't see you, I need some help to assess whether I reach you or not. So please just put some comments in the chat that I know that we are okay. Now the pH dependency of eosine is shown here, and you see now a nice feature of this tracer, and this feature is that the pH dependency is lower. So we preserve the fluorescence at pH of 4 or 5, and this is very practical in several ways. So first of all, if we measure eosine and uranine at the same time, we could actually quench now or make disappear the fluorescence of uranine and still measure eosine, number one. And then we actually restore it to 8, we measure both, and the difference can be used to actually get the concentration of eosine and uranine at the same time. And we can use eosine as a tracer in specific environments that are sour, that have higher acidity, for example in peat, or in an aquifer groundwater that has a low pH, in schist or granite. So in that case you should consider using eosine. Remember this. I might ask you, give you a certain case, describe the case and say we have low pH, or just mention it by the way, and you should then be able to actually remember that and choose eosine, because it's the better tracer under these circumstances. It's not as efficient as uranine. It doesn't have the same detection limit, but it is more stable, more conservative, more ideal under these conditions. Now, this is a summary, and we see the pH dependency of uranine, of eosine that I've just discussed, and then in addition to that, pyronine and natrium naphthionate. Summary: the most pH dependent is pyronine. Very careful when you use it. The second one is uranine. The third one is eosine. Eosine is the case for actually lower pH, 4, 5, 6. Now the least pH dependent is natrium naphthionate. It has several disadvantages. You need more tracer, it's less efficient, you have a higher detection limit. However, it is more robust. And I can tell you that we have actually evaluated the use of different artificial tracers in salt water at the coast of the Dead Sea, where we want to study mixing and dissolution processes, and naphthionate was by far the best candidate. Uranine was running into trouble in high salinity water, eosine, pyronine, but naphthionate was stable, worked perfectly. So if you have salty water, brackish water, then natrium naphthionate is actually an excellent choice. You need more of that, it's less sensitive. Another advantage is if you have a little miscalculation or you just need to use more tracer. With uranine, the result is dramatic. People will see it. It looks yellow, like in the example I gave you from Berlin. Similar pyronine, eosine, a bit less pronounced, but looks like fire or sun. It's yellowish or reddish. However, natrium naphthionate is just bluish, ultraviolet. You think something is going on here, looks a little bit strange, this water, but you do not clearly see that there is tracer in it, so it's a bit better in cases of a sensitive environment, let's say, to use natrium naphthionate. Now, the rhodamines have a low pH dependency, so for the work application of amidorhodamine and sulforhodamine in rivers, you can be less concerned about the pH dependency. You should check this, but in most rivers you have pH of 6, 7 because you have equilibrium with the CO2 system, with the atmosphere. It can go higher with 8.2 if you have algae production, but in all these pH conditions they all work perfect. So this is mainly a problem of groundwater tracer applications. Now the tinopal, photin, fluorite, they are similar. They have lower pH dependency. These are also brighteners that are quite similar to natrium naphthionate. Now you can make use of the pH dependency, as I said before, by willingly reducing the or quenching a peak, in this case of uranine. This is, for example, practical when you use uranine and pyronine together. If you understand the impact of pHD on the fluorescence and on the peak wavelength, you can actually make use of it. So the sound for me is a little bit low. The rest are perfect. Okay, I will try to speak up or to be closer to the microphone and hope that this works better now. Now, temperature dependency, we remember the 10 different cases of what makes a good artificial tracer. Now the next one is temperature dependency. The temperature dependency is expressed by this function, exponential function, and I can just show you the results. So some tracers actually have very little or no temperature dependency. So if we look at these different curves, uranine has a low temperature dependency, and so sulforhodamine as well. This is the solid curve, and the strongest temperature dependency is given by tinopal, which is not used very much anyway. So eosine is not a big deal. So usually this is not really a big problem. If you measure in tracers, or if you would do experiments in the tropics, I would double check, go back to our textbook, check the temperature dependency, maybe look up some publications, but otherwise this is not the most problematic part of your choice of tracers. Now the temperature coefficients for the curve, for the function that I have mentioned before, are given here, so you can actually calculate it and evaluate what the impact is, at least for the most important tracers. Now the sensitivity to light actually is an issue, as I have mentioned before, and you can do experiments to actually experience this or evaluate this simply by filling buckets with tracers and exposing them to sunlight. Be careful to actually use the light that actually occurs or affects your tracer during the experiment. So you cannot just expose this to lab light. You need to expose it to exactly the same light that you have in the field because of the typical spectrum of the light. So if you want to do an experiment in a river, you could actually carry out such an experiment during the tracer experiment. So prepare buckets with different tracers, different concentrations during the experiment, and measure the fluorescence before and after the experiment. So you have a real time, live, realistic measurement of the photolytic decay. Of course, you can also do experiments, but these experiments have been done. The photolytic decay is also given by an exponential formula. Intensity at time 0 times e to the power of minus k times t. You have a fluorescence decay constant that is typical for your tracer, and of course time. And these decay constants are given, so you can also express them in a half-life, which is the concentration ratio giving exactly 0.5 between initial and actual, and the half-life is given here, and you see a dichotomy or division into two parts. There are tracers that have a half-life of 6 to 11 hours, uranine and eosine. They are sensitive to sunlight. And puronine, naphthenate are also sensitive to sunlight, though a little bit less. And then you have a second group, which are the rhodamines, amidorhodamine, sulforhodamine, that have half-lives of 550 to 1300 hours. So a completely different story. While you lose half of your fluorescence at least during a day with uranine and eosine, sometimes even more, the loss of fluorescence for rhodamines, amidorhodamine, sulforhodamine is much, much lower. This is why we use the latter ones, the rhodamines, for rivers, and the first ones only for groundwater. In some cases, it might be justified and necessary even to use uranine in a river, but then you should actually calculate the decay exactly and do additional experiments to compensate for the loss of fluorescence that occurs during decay of sunlight. If you have an application, tracer application during nighttime, in some cases this works. You can actually do this. So we have done this in Italy, applied uranine in the Etch Adige river during night time, injected at 8 o'clock at night and measured 5 o'clock in the morning. Until 5 o'clock in the morning, this was perfect. This was possible. Now, the photolytic decay can be expressed if you have a half logarithmic scale here. You get straight lines, and with this diagram you can actually project or calculate the loss that occurs during a certain time. So if we go through the list of these properties, then we have discussed temperature, light, pH, detection limit. So we need to discuss sorption as well. And the result of sorption is shown here. If a tracer actually sorbs or is sorbed onto a surface, you get a delay of the peak and a kind of dispersion. This means the curve is lower, dispersed more, because the tracer is sorbed to a surface and then released. And of course this is not what you want, because you want to have a true value of your velocity, and now your estimation of tracer velocity is biased, is wrong if you have sorption. So what are the sorption properties? First of all, the process, again, you have the input of water, interaction with the porous matrix or with the surface. This can be first order kinetic reactions or irreversible first order reactions whatsoever, and they affect the breakthrough curve. And this affects your use of tracers to actually assess hydrological systems. Now, an ideal tracer will not sorb. This is number one. You may have an equilibrium reaction, so actually your tracer will appear later, but you will not lose tracer. You might also really lose tracer by irreversible reactions. So the chemistry of the absorption reaction actually is important and plays a role. So is it irreversible? Is it reversible? Is it first order, second order? Is there absorption to one side or to several sides? But at this stage, before we actually discuss modeling, we just want to know what are the tracers that are not sorbed. Now, this is an experiment that we have carried out in Freiburg at the university, where we have compared Euro9, almost perfect tracer, to deuterium, perfect tracer. Deuterium is just water, deuterated water. This is water. So if we use deuterium and we measure it with a mass spectrometer, we can actually measure water. Remember, deuterated water is an artificial tracer, but it's expensive. Liter, I don't know, 1 liter or 2 liters cost 3,000–4,000 euro. So quite expensive. Now, this was an experiment that we did in a column in the lab, and you see that actually Euro9 and deuterium behave exactly the same way. You see how the tracer travels through sand of a column. After half a meter, 1 meter, 1 meter 50, there is dispersion. The dispersion is like textbook-like advection dispersion equation. There is a little difference in the concentration, which is mainly due to the design of the experiment. It's not related to sorption. You see the time of the peak is exactly the same. So Euro9 behaves almost like a perfect tracer. Deuterium, of course, as well. This was the experiment to actually evaluate the test. If you do research and you actually want to work on the estimation of velocities and really try to avoid any bias, and you need to justify and thoroughly prove what you do, it's wise to do parallel column experiments in your laboratory and to double check whether the tracer works in that sediment and with the water type, for example, at a higher salinity, at a low pH, with high dissolved organic carbon in a polluted water, and so on. And you should do actually these parallel experiments to validate your field experiment. Now, a very simple measure to detect whether your tracer works is to use the recovery. So the recovery is obtained by simply summing up the concentrations over time and multiplying them with the flow. So flow times concentration is a mass, and if you sum it up, if you build the integral of the concentrations over time multiplied with the flow at that concentration, in the most ideal case it's a constant flow, you get the mass, and you can compare the mass recovery to the mass injection, because you inject a certain amount of tracer. Now, you should get 100% back. This is the case number one, ideal tracer. But sometimes you don't get everything back. So this is case 3 and 4. In that case, you had a first order kinetic reaction or a two-side reaction, actually keeping some of the tracer to the surface permanently. Now, if you have an instantaneous equilibrium reaction, you will actually get everything back with a certain delay. So by comparing injected mass to recovered mass, and also by comparing the shape of the recovery curve, you can validate whether your experiment is correct first, and second, which type of reaction may have affected your experiment. So there was a question, how can we differentiate natural deuterium from the artificial deuterium? We cannot, in fact. This is just differentiated by the concentration. So usually deuterium values in normal water are like -100 per mil, which means that we have 100 per mil deviation from the standard. And the standard is, as you may remember from the first lecture, 105 or so, 155 molecules of deuterium per a million of molecules of water. In fact, to be precise, a million minus 155, because we talk about the ratio. So of isotopes. So this is the standard that we have, about 150 molecules per million in our natural sample, and from that we observe a deviation of like 100 per mil in normal water. Now, if we actually use pure deuterated water, we will get a very high concentration of deuterium in water that can be clearly distinguished from the natural background. This was regarding the question. Now, this is a difficult topic because sometimes we really observe that the recovery is not perfect. Why? It can be because, first of all, we did not catch or measure the plume. So part of the plume was actually tangential to our problem. I will switch again to the desk to demonstrate and to draw this. That's a little mess, but I hope you forgive me. Just take a little second until we have the until you see this. So I will already draw an injection plume, and we assume that we have a trace experiment where we inject a tracer into a groundwater and we now measure. And of course, in order to calculate the recovery curve, we need discharge. Discharge can be wrong. We make a wrong assumption about discharge, then we also get a wrong recovery curve. But it's also possible that we measure just the fringe, the border of our plume, and therefore we underestimate the real concentration. Most of the tracer, most of the plume, most of the concentration is actually not going through our borehole, observation borehole. This would be the injection borehole. So if we don't know this and assume that this is the main plume, the main concentration, because we have measured something, but we don't know that the real concentration is much higher, a little bit further to the center of the plume, we get the wrong recovery calculation, of course. So this can be the case. But it can also be the case that part of the trace is stuck, and this happens often when we try to make trace experiments through the unsaturated zone. Then tracer actually gets into pores, gets stuck there, is released slowly, but we don't get a full recovery. And from my experience, when we make trace experiments through soils, through unsaturated zones, we lose a lot of tracer. I would say a factor of 10. So we get just 1/10 of what we injected out of the experiment. So be careful when you do trace experiments through the unsaturated zone, and be prepared to lose a significant amount of that tracer in the unsaturated zone. I would advise, but this is already now for tomorrow and day after tomorrow, to always do 2 experiments. So one for the unsaturated zone, just focusing on the transfer from top to bottom to the unsaturated zone. If this fails, okay, you can repeat it. It's a small scale experiment. And the second one from groundwater beneath the unsaturated zone actually to your borehole. So if you split this into 2, you can repeat one part of it, and if you fail, you just fail. You have a partial failure. This is also helpful to actually have both transfer times to the soil and then from the bottom of the soil to your borehole. Okay, now more or less 15 minutes to go, and then we'll finish. So we still have 29 students, so we just lost 4 or 5. This is okay. It's still a pity. The absorption is measured using the distribution coefficient KD, and this describes how much is actually on the surface of the aquifer or of the soil compared to what you've got in this solution. Now it's calculated from the initial tracer concentration minus the dissolved tracer concentration divided by the dissolved. So the first part is actually what is on the soil. The second one is what is in the water. This gives you a value, a KD value, that tells you how much is stuck on the soil. So 5 means 5 times the amount on the soil. Now this can be translated into a retardation factor quite easily. So if you have a KD value, then you can convert this to a retardation factor, and the formula for the calculation of the retardation factor as a function of the porosity NE, effective porosity, and the KD value, so the distribution factor, and the bulk density is given below. You might have seen this equation before. So the retardation factor is actually the ratio of the velocity to the true velocity, and it can be calculated from soil properties using the parameters density, bulk density, effective porosity, and distribution factor KD. Now the KD values are given here for different fluorescent dyes, and the first one that we will actually watch is Euro 9. Remember here that we have 1 plus, so we actually have, by this definition, a true value given by the value 0. And if we have a positive value, it means that we get a retardation. So Euro 9 is perfect tracer, as we have shown before, over several over a range of concentrations. Now we see immediately that sulfurrhodamine, amidorhodamine has significant retardation, or has a higher KD value, and you see that naphthionate, puronine, eosine are closer to ideal conditions, although not perfect. So if you can use Euro 9, naphthionate, puronine, eosine are okay. You have to make compromises. Eosine is good for low pH. Puronine is good if you want to quench it and use it with another tracer. Naphthionate has the advantage of a separate emission excitation spectrum, a bit less visible, although less efficient. So they are all okay for groundwater. Amidorhodamine, sulforhodamine, no way. They will simply get stuck to your soil and be sorbed so much that you cannot use the experiment by any means to estimate flow velocities. So the measured retardation coefficients are given here. Same story. So they should be 1 in the ideal case. They are 1 for uranine at different concentrations. Eosine is quite close to 1. Also pyranine is okay. Amidorhodamine, you see retardation 2.7, so it's like 3 times slower, but it can go up to 22 times slower, 30 times slower. So actually useless, pointless to be used in an aquifer. Now the last one, but not least one, and we are approaching the end of the first lecture, is the toxicity. Now, the toxicity of these substances has been investigated by Behrens. There is a famous paper that he prepared for Umweltbundesamt, and I strongly advise you to attach this paper to any trace experiment or permit application that you do, because you can actually avoid many discussions by doing it. In this paper, the toxicity has been evaluated based on medical clinical studies, on evidence so far gained. There are many clinical studies because these traces are also used in a clinical context to trace cells or to mark cells. So they have studied the impact of these substances, which is good for us. And the result is that uranine is safe, that eosine is safe, and many are safe. For example, amidorhodamine is safe, important. Pyranine, tinopal are safe. Lithium, strontium, bromides, the salts are safe with restriction. Lithium is also used as a medical substance, especially for psychiatric applications. So it has an impact on our mood. So it has an impact, but it is not cancerogenic, but I would limit the use. The same for bromide, strontium. So to cut a long story short, uranine, eosine, pyranine, naphthionate, tinopal are okay to use, but you should not use rhodamine WT, you should not use rhodamine B, and not use rhodamine 6G. The amidorhodamine or sulforhodamine are amidorhodamine is a different story. This is okay. Sulforhodamine is ecotoxicologically unsafe. So it has an impact and may have an impact on microbiological organisms in a river. So there is no significant risk for humans. So this leaves us with amidorhodamine G as the best tracer for rivers. I have attached the paper. It's in the learning room, Moodle. So you see it there, and you can download it and use it and attach it to permits that you prepare for trace experiments. So we can now summarize everything, the tracer properties, and actually look at these 10 dimensions. And this gives us then a set of traces that we can use for porous groundwater, for karst groundwater, fissured groundwater, surface water, and glaciated areas. And this is the knowledge that you should have after the first day. You should be able to select a tracer based on these 10 criteria. You should know the criteria. I mean, we will not have an exam, so I will not ask you to list the 10 criteria, but you should know where the slide is and be able to use them fully to choose the best tracer in your case, taking into account pH, temperature, photolytic behavior, and the emission excitation properties of the tracer, in addition to detection limit and toxicity. Now, there is some material on how to measure tracers. Basically, we have old traditional methods, visual inspection, still used a lot by engineers, fluoroscope, which is not used anymore, and optical fluorometers. They all use the same principle, that the intensity is related to the tracer concentration through this formula. So we try to neglect or assume constant the other elements and try to establish a relationship between intensity and tracer concentration, basically. Now, today you can buy filter fluorometers on the market, and in a good lab you should have a spectral fluorometer which is able to actually produce wavelengths at different parts of the spectrum, plus a sensor that is able to detect the light intensity at different wavelengths. You can actually combine this with a fiber optic cable to actually measure at an identified point, and these cables can be up to 600 meters long and give you the possibility to measure down in a mine or in a very deep borehole, so to actually get the light down there and bring it up there through fiber optic cables. This is how a spectral fluorometer looks like. This is an old one, Perkin-Elmer. You have now several producers producing them. It's basically a peristaltic pump. It's an optical system, and you scan through the wavelengths and measure the emitted wavelength with this system. Usually you have a computer with which you can program and go through all your samples. Now, this is the principle. You have the lamp. The lamp sheds light on the sample, and you measure usually with a 90 degree angle to avoid direct scattering or absorption or reflection, and just get the fluorescence. And the fluorescence is then going again through a filter or through a monochromator, which is a prisma, to the detector. There are some nice field devices like the GGAN, this is the name, GGAN from Switzerland, with which you can measure in rivers or in boreholes, which are basically filter fluorometers. So you produce light with an LED lamp, and this is in a cavity or in a measuring cell, which can be large like this one for a river or small for a borehole, and you get the light signal and the data logger to store it. You have these devices, fiber optic fluorometers, which have the advantage that they bring the light from the lamp, which is expensive, sensitive to temperature, doesn't like water, into the water through a fiber optic cable. And these are basically just lamps and mirrors to get the signal back to the device and to the sensor. So in a fiber optic fluorometer, you just separate the lamp from the water and for input-output. So your different devices can be applied. You should mention how you measure in a permit application. So the best solution is always to use with a spectral fluorometer, which is about 30 to 50,000. If you cannot afford this, you should at least have a filter fluorometer that is suitable and understand the chemistry of your measurement, namely the pH dependency. Another interesting possibility is to use so-called fluorocapteur. This is a French word, which can be just a tea bag or these metal balls in which you put activated carbon, charcoal, that can absorb actually fluorescent dyes. So you put them into the water and they collect fluorescent dyes over a certain amount of time. You can just come back after a week or a month and detect, wash it or retrieve it or leach it from that substance, and then measure the fluorescence to have a detection, yes, no, has there been any trace of tracer. This is good in combination with trace experiments to check that you didn't lose anything, that nothing came out of a spring unobserved. So I think we should stop here. If there are some slides left, we'll deal with this tomorrow, because we now go into salts and pollen. I can just start with this tomorrow with a small review. And I would just ask you to give me a small feedback on the lecture today, whether this was interesting for you, whether the speed and sound, the conditions were okay finally, and whether you could follow. So I would be happy to have your feedback to see how we can actually improve the transmission of information to you. So I would be glad to just get some feedback. I invite you to go through the text. So I will prepare an exercise on tracer selection and upload it. So ask you some questions that you can actually answer. So if you want to check, it should be ready at 5 p.m. or you can do this tomorrow before the lecture, and I will have the next lecture, or we will have the next lecture tomorrow at 10. Now, if the system worked fine for you, we have this as a safe option, but I would like to have more communication with you, so to get more response from you, more direct response questions. So I will try to set up a system that works better. If not, in any case, you have a live stream lecture for tomorrow. I will put the live stream lecture online. I will cut some of the beginning, which was just picture without sound, and then the lecture will be linked from the e-learning module to the YouTube page, and the video, the live stream, will be unlisted. So you can just access it through the e-learning space, but not find it directly on YouTube anymore. Okay. I would be happy to have some feedback, and I hope to see you again tomorrow at 10 o'clock. Yeah, okay. Yes, so organization and system. So anyway, if this system is okay as a baseline for you, we'll have the same system tomorrow. And so to be safe, not to have a delay again. And I suggest that then we do this, and then I have more time to prepare an environment where we have interaction, because we definitely need this for Wednesday. If you have any further questions regarding the organization of the course, or questions how the exam will be done, you can also ask these questions in the news forum, and I will answer them before the lecture tomorrow. So have a nice evening, and see you tomorrow.